Hey everyone, Miss Butler here. I'm super excited because we are going to start electrochemistry today. And what is electrochemistry? Well, it's looking at chemical reactions and a specific type of reaction that involves a transfer of electrons. So we're going to hone in on these reactions where an electron is transferred from one of the substances to the other. And so this video is going to be all about these reactions. As an introduction, we call them REDOX or oxidation reduction reactions. So this is a little introduction. So in regular chem, you guys learned about different types of reactions. So synthesis is when we have two or more reactants forming one product. Decomposition is when we have one reactant breaking down either into the elements or into smaller pieces. Single replacement, I have a single element by itself in the standard state, an ionic compound, and then we're going to have that kind of a swap or a date swap. And so we have a new ionic compound and a new element in its standard state. And then we have combustion, where we have a hydrocarbon, so some number of carbon bonded to some number of hydrogen reacts with oxygen to make CO2 and H2O. All of these reactions that you learned about in regular chem are actually redox reactions. So that means one thing is being oxidized, one thing is being reduced, and those vocab words you haven't heard is just a fancy way of saying an electron is being transferred from one of the items to another. Okay? When there is a change in the charge or the oxidation numbers, we call it a redox reaction. Notice there is one type of reaction from regular chem that's missing, and that's a double replacement, where we have an ionic compound and an ionic compound and they trade partners. When we have a double replacement reaction, none of the atoms change charges, and so that is not considered a redox reaction, but synthesis, decomposition, single replacement, and combustion are all examples of redox reactions. So when we're looking at redox reactions, we know an electron's being transferred, so it's really nice to have a way to keep track of these charges, because if a charge changes, that means an electron was either gained or lost. So how we do that, how do we keep track of these electrons moving, is we assign every part of a reaction an oxidation number. And so that's the assigned charge of an atom, and it will help us keep track of things as we look at these reactions. So if I'm looking at a chemical formula, how do I actually assign oxidation numbers? There are some rules to help us. So the oxidation number of an uncombined atom is 0. So for example, aluminum in its standard state is solid. That will have an oxidation number of 0. Copper in its standard state is a solid all by itself. That will have an oxidation number of 0. The oxidation number for a monatomic ion. So if I have aluminum, but it's in its aqueous ionic form, 3+, we'll have an oxidation number of +3. If I have fluorine with a -1 charge, that will have a oxidation number of -1. If you have a debate and two things are bonded, the atom that has the more electronegativity or higher electronegativity, that atom will keep its charge. So for example, if fluorine is in a compound and there's some conflicting rules as we keep going, fluorine will be the one who wins and gets to keep its charge and have an oxidation number of -1. So we'll look at examples of this. Oxygen usually will have a -2 oxidation number unless it's in a peroxide, and peroxide is a polyatomic ion that is O2 with a -2 charge. And so if we have a peroxide, so hydrogen peroxide, H2O2, in that case, the oxygen will have a -1. So yes, overall peroxide has a charge of -2. Each oxygen has an oxidation number of that -1. Okay, and then if it's bonded to fluorine, fluorine's going to dominate in that case. So fluorine will have then fluorine will be -1 and oxygen will be +2. So again, oxygen 9 times out of 10, actually probably 99 out of 100 is going to be -2. Couple exceptions where oxygen could be -1 or it could be +2. Hydrogen, this is a good one. Hydrogen is going to have a +1 oxidation number, okay? And there's a couple exceptions that we don't really see too often where it could possibly be a -1. Again, probably in this case, 999 times out of 1,000, hydrogen is going to be +1. And then here's a big one. The total charge of a compound or polyatomic ion must sum up all of the oxidation numbers must sum up to the charge of that compound. So if I have something neutral, all of the oxidation numbers for the elements that make up that neutral chemical, they all have to add up to 0. So they have to cancel each other out. If I have a polyatomic ion like nitrate, NO3, with a -1 charge, the oxidation number of the oxygens need to cancel out and add up with the nitrogen to a -1 value. Okay, so let's look at assigning these. All right, let's start to assign. So I see that CO2 is my first one. And so in this problem, we know oxygen is -2. That was one of my rules, and it's not one of the exceptions. But if you look, there are two oxygen atoms. And so really oxygen with each being a -2, that is contributing a -4 overall. Okay, and this chemical is neutral, no charge. I don't see a charge. So that means the one carbon has to cancel out that -4. So that one carbon must have an oxidation number of +4. So what's my final answer? My final answer here, grab my highlighter, is going to be these right here. So oxygen has an oxidation state of -2. The carbon has an oxidation state of +4. This 4 down here, this -4, was just helping me figure out what carbon needed to be because each oxygen is a -2 and there's 2 of them. So to make it neutral, my oxidation state of this one carbon had to be +4. Let's check out this guy, SF6. Well, we know fluorine is going to be a -1, and there's 6 of those, so that's contributing -6. There's only one sulfur, so that sulfur, in order to make the chemical neutral, must have an oxidation state of +6. So my oxidation numbers are sulfur is +6 and fluorine is -1. Why don't you pause the video and try the next ones? We have NO3 minus, so the oxidation numbers must add up to that -1. We have SO3, N2O5, and SO4 -2. Pause the video and try those. And then I also want you to try this challenge one, K2CR2O7. My tip for big molecules like this is I usually work from the outside towards the middle. So I'm going to assign oxygen's numbers, and I'm going to assign potassium's numbers, and then this middle guy I will do last. If there's not a rule for it, like potassium, right, or nitrogen, usually what you can do is you can either go off of what you know, like so for this nitrogen, I'm going to go off of oxygen and then figure out what nitrogen needs to be to make it neutral. But in this case, if I assign oxygen and I still don't know K or chromium, I'm going to look at the periodic table and take the charge of potassium. So give these a try and then we'll check. All right, so NO3 -1, I have -2 for the oxygens, but there's 3 of those, so that's contributing -6. So nitrogen must be +5, so that way +5 and -6 give us that negative charge. Same thing here, we have -2 for oxygen, so the sulfur must be a +6. We have a -2 for the oxygen, so that means these nitrogens, because there's 5 of them, these are -10. The nitrogens have to contribute a +10, but there's 2, so each nitrogen has to be a +5. And then over here, I got a -2 for the oxygen and a +6 because they need to add up to a -2. Here's the challenge one. Let's work from the outside. Oxygen is a -2, and there's 7 of those, so that's going to be -14. Potassium's a +1, so that contributes a +2. So right now I have a -14 and a +2, so what does the chromium need to be? Well, it needs to add up to a +12, and there's 2 of those, so a +6 is the oxidation number for chromium. It is possible to have non-integer, meaning fraction oxidation states. It is rare, but I want you to see an example just in case. So why don't you pause the video and try this, knowing that one of these elements will have a fraction as its oxidation number. All right, so I have oxygen at -2, so that contributes a -8. That means I need iron to be a +8, and there's 3 of those. So that means each iron must be a +8/3. So the oxidation state for iron is +8/3, +8/3. Now that we know how to get oxidation numbers or record oxidation numbers, we're going to look at full reactions and see what's happening. So if we have a balanced equation and one of the elements loses electrons, we call that oxidations. And remember, electrons are negatively charged, so if I lose electrons, the charge of that element should go up. Okay, so if it loses electrons, the charge is going to increase from the reactants to the product side. That's called oxidation. Reduction is when you gain electrons, and that's because there's a reduction in charge. Electrons are negative, which makes the charge go down. So if the charge goes down, that element gained electrons, we call it reduction. How do I remember this? There's a couple ways. Oil rig is an expression. So oxidation is losing, reduction is gaining. So oxidation is losing electrons, reduction is gaining. My personal favorite is Leo the lion says grr. So Leo says grr, loss of electrons, oxidation, gain electrons, reduction. So those are two little ways for you to remember. All right, here's what I would like you to do. I want you to assign oxidation numbers. Remember, things in their standard states are 0. So assign oxidation numbers to every part of these equations, and then we're going to look and see what is oxidized and what's reduced. So pause the video and put a little oxidation number under every single element, every single capital letter, and then let's check and see who's oxidized and who's reduced. All right, hopefully you got 0, 0, plus 2 for the copper, minus 2 for the oxygen. So notice these big numbers in the balanced equation don't matter. We just look at the chemical formula and the subscripts to assign oxidation numbers. So copper started at an oxidation state of 0 and went to an oxidation state of plus 2. And so that means it lost electrons because it got a bigger charge. Electrons are negative. When we lose electrons, that's Leo the lion, Leo lost electrons, oxidation. Oxygen went from 0 to a minus 2. So 0 minus 2, that's gaining negative electrons. So it is reduced. So gain electrons, gain electrons, reduced. And then we have 0, 0, plus 1, minus 1. So the cesium went from 0 to plus 1. That lost electrons and is oxidized. The fluorine went from 0 to negative 1. It gained electrons. It was reduced in this balanced equation. Okay, your book might ask you about what is the oxidizing agent and what is the reducing agent. And so the oxidizing agent is the one that causes oxidation. So whatever is reduced is going to be the one that caused the other thing to be oxidized. So we actually call the thing that was reduced, we call it the oxidizing agent. But that's usually going to be the entire chemical. So in that last problem, for example, we had Cu plus O2 makes CuO. And we said the copper was oxidized and oxygen was reduced. In this case, my copper would be my reducing agent, and my oxidizing agent, that's the one that does the reducing, oxidizing, I think I'm missing a Z in there, work with me, is O2. So here's kind of the tricky part. It feels opposite. If something's reduced, it's called the oxidizing agent. If something is oxidized, we call it the reducing agent. Okay? But instead of just saying the elements like Cu and O, we give the full formula. So in this case, copper was reduced and copper was oxidized and copper was the reducing agent. Oxygen, the element, was reduced, and O2, that chemical, was the oxidizing agent. Okay? So if it's reduced, it's the oxidizing agent. If it's oxidized, it's the reducing agent, but we give the full chemical formula. All right, when powdered aluminum metal is mixed with pulverized iodine crystals and a drop of water is added to help the reaction get started, the resulting reaction produces a great deal of energy. The mixture bursts into flames and a pure smoke of I2 vapor is produced from the excess iodine. The equation for the reaction is, there you go. For this reaction, identify the atoms that are oxidized, reduced, and tell me the chemicals that are the oxidizing and reducing agents. So I would like you to assign oxidation numbers I2, and this is I3, capital A, capital I at the end. I want you to do the oxidation numbers, tell me what element is oxidized, what element is reduced, and then what chemical formula is the oxidizing agent and what chemical formula is the reducing agent. I'm going to put the answer up in 3, 2, 1. All right, check your answers. Hopefully you figured out that aluminum is oxidized, so aluminum is the reducing agent, and that iodine is reduced, so I2 is the oxidizing agent. Check your oxidation numbers if your answer does not match mine. We'll go over some of this in class this week.